A captured American tank rolled onto the proving ground at Kummersdorf, south of Berlin, in the summer of 1943. It had journeyed across thousands of miles, first through combat in the Tunisian desert, then by ship across an ocean, and finally by land over rough European roads. The vehicle bore the marks of conflict. Dust still caked its tracks, desert sun had bleached its paint, and small arms fire had pitted its hull. Yet, when a technician climbed into the driver's seat and engaged the starter, the engine fired almost immediately. The Continental radial coughed once, then settled into a steady, confident rumble. The German engineers gathered their exchanged uneasy glances. Their own formidable Panther and Tiger tanks, designed for unparalleled combat prowess, frequently failed during road marches to the front. Transmissions stripped, final drives broke apart, and engines consistently overheated. This enemy machine, however, had endured over 5,000 miles of operations across North Africa and was still running as if new. An order quickly went out for its complete disassembly. Every component, every rivet, every bolt would be meticulously examined, measured, and documented. What the engineers uncovered within its sturdy frame would begin to dismantle their deeply held convictions about the very nature of armored warfare. Simultaneously, more than 6,000 miles away, workers on the night shift in a factory near Detroit were constructing another Sherman tank. They would complete its assembly in less than a day. By the time the German engineers at Kummersdorf finalized their comprehensive report, American factories would have added another 1,000 tanks, just like it, to the Allied arsenal. German designers were convinced they crafted the world's most advanced fighting machines. The Americans, in contrast, were demonstrating that the tank that prevailed in battle was not necessarily the most powerful, but rather the one that consistently arrived at the fight. This fundamental misunderstanding stemmed from deeply divergent philosophies of design and industrial production that predated the war itself. German engineering tradition prized complexity, meticulous precision, and theoretical perfection. The same nation that produced Mercedes-Benz automobiles and Zeiss optical instruments applied those rigorous standards to its military hardware. Each tank was envisioned as a masterpiece, an intricate blend of the most potent weaponry, the thickest armor, and the most sophisticated fire control systems then available. The Tiger tank served as the ultimate expression of this doctrine. When it entered service in August of 1942, it stood as the most formidable armored vehicle on any battlefield. Weighing 57 tons, it mounted the fearsome 88mm gun, adapted from a renowned anti-aircraft weapon, and boasted armor up to 100mm thick on its turret front, with a mantlet reaching 120mm. In a direct confrontation, a Tiger could neutralize any Allied tank at ranges exceeding 2,000 meters, while remaining virtually immune to incoming fire. The Panther, which first saw combat in July of 1943, combined exceptional firepower with enhanced mobility. Its high-velocity, 75mm gun could penetrate 111mm of angled armor at 1,000 meters. Its sloped frontal armor, an adaptation inspired by the Soviet T-34, offer protection equivalent to much thicker vertical plating. German engineers widely considered it the finest medium tank design of the entire conflict. These vehicles instilled terror in Allied tank crews. American tankers ominously refer to the Tiger as the monster, recounting how their shells would harmlessly deflect off its armor, while return fire would tear through their Shermans as if they were made of paper. The psychological dominance exerted by German heavy tanks fostered a mythology of inherent superiority that endures even today. German engineers, examining the Sherman, saw a machine that appeared to violate every principle they held sacred. The American tank weighed a mere 33 tons. Its 75mm main gun, while adequate against older German models like the Panzer III and Panzer IV, often struggled to penetrate the frontal armor of Panthers and Tigers at typical combat ranges. Its own armor, varying from 50 to 76mm depending on the specific variant and production date, was susceptible to penetration by the standard German 75 mm gun at battle distances. Its prominent silhouette made it an easy target on the battlefield. On paper, the Sherman seemed definitively outmatched in every critical category. This assessment was not without reason, given the established metrics German engineers used to evaluate armored vehicles. German armor consistently achieved tactical victories throughout the war. A single Tiger, skillfully crewed, could and often did eliminate multiple American tanks before being eventually neutralized. The kill ratios in individual engagements frequently favored German armor by margins of 3-1 or even higher. A German officer, Michael Wittmann, a celebrated tank ace of the war, was credited with destroying more than 130 enemy vehicles during his career, many of them Shermans. Yet, this German analysis harbored a critical, overlooked flaw. They evaluated the Sherman solely by the standards of individual tank-on-tank combat. They failed to apply the broader standards of industrial warfare. They meticulously counted gun calibers and armor thicknesses. They did not factor in factory floor space or global shipping capacity. They calculated penetration values with precision, but ignored the rates at which replacements could be produced. The particular Sherman that arrived at Kummersdorf had been seized near Spitla, Tunisia, on February 22, 1943. It was an M4A1 variant, identifiable by its cast hull, one of 134 such machines manufactured by the Lima Locomotive Works in Ohio during July of 1942. Its United States Army registration number was 306-7641. A reconnaissance patrol from the Schwer Panzerabteilung 501 had discovered abandoned but otherwise intact amidst the disarray of the Kasserine Pass offensive. American forces had retreated so rapidly that substantial quantities of equipment were left scattered across the desert. Recognizing the significant intelligence value of a serviceable enemy tank, the Germans transported it 350 kilometers overland to Tunis, a demanding journey that consumed 4.5 days over treacherous roads. From there, it was shipped to Germany, where it was assigned the military registration WH-05894117 and the testing designation Versuchsfahrzeug number 259. The Kummersdorf facility had served as the primary testing ground for the German army since 1875. Its engineers had evaluated the first German tanks during the Great War, tested the early panzers that spearheaded the conquest of France, and meticulously examined captured French, British, and Soviet equipment throughout the current conflict. They approached the Sherman with the systematic thoroughness characteristic of German technical work. The process began with static analysis. Engineers carefully measured every armor plate, stenciling its precise thickness in millimeters directly onto the hull with white paint. The vehicle was photographed from every conceivable angle, documenting battle damage and were patterns that provided clues about its operational history. They noted that the tracks, though significantly worn, remained fully functional, that the engine compartment, while dusty, showed signs of diligent maintenance, and that the main gun, despite evidence of repeated firing, exhibited no excessive erosion. Next came functional testing. The Germans drove the Sherman extensively around the Kummersdorf proving ground for several days, subjecting it to the identical rigorous trials they applied to their own vehicles. A 1-kilometer hilly track assessed suspension performance and engine endurance. Cross-country courses evaluated its mobility across challenging terrain. Speed trials measured its acceleration and maximum velocity. At every stage, the Sherman performed within its original specifications, despite thousands of miles of previous use in combat. The ballistic tests, however, yielded results that initially appeared to confirm German assumptions regarding the Sherman's vulnerability. Utilizing armor plates identical in composition and thickness to the Sherman's hull and turret, German gunners meticulously determined the penetration ranges for their standard anti-tank weaponry. The 88mm gun of the Tiger could penetrate the Sherman's differential housing from 2,100 meters and its turret front from 1,800 meters. The Panther's high-velocity 75mm gun achieved comparable results. German gunners could, therefore, destroy Shermans at ranges where the American tank's own weapon posed little reciprocal threat. But then, an unexpected discovery emerged when the Germans tested the Sherman's upper glacis plate under conditions simulating actual combat. When the tank was positioned at a 30-degree angle from perpendicular, a common scenario where a vehicle is not facing its attacker head-on, the combined effect of the glacis slope and this horizontal rotation produced an effective armor thickness exceeding 100 millimeters. Under these specific conditions, the Tiger's 88 millimeters gun was unable to penetrate this surface at any range. Even the Panther's superior gun required the Sherman to be facing directly forward to achieve penetration of the upper hull. This finding, while significant, did not fundamentally alter German tactical doctrine. Tank commanders were already trained to maneuver for flank and rear shots against enemy armor, regardless of the specific vehicle. The Sherman's side and rear armor remained vulnerable, and its turret could still be penetrated at typical combat ranges. Yet the glacis test offered a glimpse into a design philosophy the German engineers had not fully grasped. American designers had given considerable thought to how tanks actually engaged in combat, not merely how they performed on a technical specification sheet. The more profound insights, however, came during the examination of the Sherman's mechanical systems. Here, the divergence between German and American design philosophies became strikingly apparent, revealing a cascade of interconnected problems for German forces. The first surprise was the gyroscopic gun stabilizer. No German tank possessed anything remotely similar. The Westinghouse system employed a spinning gyroscope to detect the vertical movement of the tank, automatically adjusting the gun's elevation to compensate. Its rotor spun at over 12,000 revolutions per minute, providing a stable reference point regardless of the hull's erratic motion. Electric motors connected to the gun mount reacted to signals from the gyroscope, maintaining the barrel's aim on the same spot in space even as the tank pitched over uneven ground. A Sherman crew could engage targets while moving at 15 miles per hour with approximately 70% accuracy at ranges up to 300 yards. While accuracy diminished at longer distances, the capacity to fire on the move provided an immediate, substantial tactical advantage. German tanks, by contrast, were forced to halt to fire with precision. In the chaotic, rapidly shifting environment of mobile warfare, the ability to engage while advancing meant a Sherman could press forward under fire, engaging targets as it closed the distance, while a Panther or Tiger had to choose between firing and relocating, a choice that could prove fatal. German engineers meticulously photographed the stabilizer mechanism, documenting its components: the gyroscope housing, elevation motor, control unit, and power supply, with their characteristic precision. They traced electrical connections and measured response times. The entire mechanism operated on a mere 24-volt electrical current. Yet, despite this thorough analysis, Germany never deployed an operational tank gun stabilizer during the war. The immense engineering resources and manufacturing capacity required to develop and produce such systems at scale were already fully committed to other critical wartime priorities, creating an unforeseen limitation. The second surprise revolved around the standardization of parts. The Sherman's designers had integrated interchangeability into the vehicle from its inception, following the mass production principles American industry had refined over decades. Any suspension bogie from any of the 11 American manufacturing facilities could be unbolted and seamlessly fitted to any other Sherman. The same applied to road wheels, track links, drive sprockets, idler wheels, engines, transmissions, and virtually every other major component. This standardization extended beyond individual tanks to the entire fleet. A Sherman constructed by Chrysler in Detroit used identical parts to one built by Fisher in Grand Blanc, or Press Steel in Chicago, or Lima Locomotive in Ohio. Supply officers could requisition components without needing to specify which factory had originally built the vehicles they were supporting. Parts could be scavenged from damaged or destroyed tanks and used to repair others, irrespective of their origin. A supply depot in France could receive shipments from any American factory and distribute them to any American unit without concern for compatibility. The logistical ramifications were profound. Instead of painstakingly tracking thousands of unique part numbers for each factory and production batch, American quartermasters managed a unified inventory. Instead of maintaining separate supply chains for each manufacturer, they operated a single, cohesive system that served everyone. This simplification cascaded through every level of military organization, from the vast depots to individual tank crews, creating an unprecedented efficiency that became a persistent, grinding problem for their German adversaries. German tank production, conversely, adhered to a different model. Each manufacturer fabricated components to its own specific dimensions, employing its unique tooling and its individual interpretation of design blueprints. A transmission from one factory might not fit a tank from another without extensive modification. Even within a single production run, variations accumulated as designs were subtly altered and improved based on combat experience and engineering refinements. A Tiger built in January might require different parts than one assembled in March. This created a logistical nightmare, a problem that worsened as the war progressed and production was increasingly dispersed to evade Allied bombing campaigns. Spare parts for a specific tank variant might exist in a depot hundreds of kilometers away, while the vehicle itself sat immobilized, awaiting a single, elusive component. Supply officers had to track not just tank types, but specific production batches and manufacturing dates when requesting replacement parts, adding layers of complexity to an already strained system. This escalating logistical fragility continuously undermined the perceived mechanical superiority of their machines. The third surprise was the unparalleled ease of field repair. American designers had anticipated that tanks would inevitably break down under the relentless stress of combat operations, and that repairs would most often need to occur close to the front lines, rather than in distant rear area workshops. They engineered the Sherman so that major components could be removed and replaced by ordinary soldiers using only basic tools. The transmission and final drive assembly, for instance, bolted directly to the front hull in a configuration that allowed the entire unit to be extracted simply by unbolting it from outside the vehicle. A field maintenance crew could remove a damaged transmission, install a replacement, and return the tank to service within a matter of hours. No cranes were required, no specialized equipment beyond standard military-issue tools. The work could be performed in a simple farmyard or a forest clearing, even with the front lines just over the horizon. The Panther's transmission, by contrast, was deeply embedded within the hull, accessible only from inside the vehicle through cramped, narrow passages that rendered work difficult and agonizingly slow. Replacing it necessitated removing the turret, extracting the engine, and then laboring in highly confined spaces to disconnect and remove the transmission components. This process demanded specialized equipment, highly trained mechanics, and workshop facilities that existed only in secure rear areas. A Panther that threw a track or stripped a gear in the field might be out of action for days, or even weeks, awaiting recovery and repair. The Tiger was even more problematic. Its sheer complexity meant that field repairs were often impossible. Damaged vehicles had to be laboriously towed back to major maintenance facilities, assuming recovery vehicles powerful enough to move a 57-ton tank were even available. Standard German recovery vehicles were simply inadequate for the Tiger's weight. Specialized Birch Panther recovery tanks were developed, but these too frequently suffered from their own mechanical problems. Many Tigers were lost not to enemy fire, but to breakdowns that could not be rectified before advancing enemy forces inevitably overran their positions. This stark contrast in maintenance philosophy fundamentally shaped the entire conduct of armored warfare. American units pushed forward with confidence, knowing that broken tanks could be swiftly repaired and returned to action. German units, conversely, hesitated to advance too far from their repair facilities, understanding that breakdowns in forward areas often meant the permanent loss of invaluable vehicles. The Sherman's reliability was not merely a mechanical attribute. It was a potent tactical advantage that influenced every decision commanders made, creating a persistent pressure on German operations. The German engineers compiled their findings into a technical report that meticulously documented every lesson learned. They accurately noted the Sherman's vulnerabilities. Its armor was thin by German standards, its gun was underpowered against modern German tanks, and its high silhouette made it an easy target at long range. In a one-on-one engagement with a Tiger or Panther, the Sherman would likely be destroyed. Yet, embedded within the dense technical details was a more unsettling observation, one the report's authors may not have fully grasped at the time. The Sherman was simple. The Sherman was reliable. The Sherman could be constructed by workers who had never before seen a tank, utilizing standardized parts sourced from factories spread across an entire continent. The Sherman could be shipped across an ocean, driven off a landing craft onto a North African beach, and maintained by mechanics working in muddy fields with basic tools. The German engineers, in their methodical way, understood the implications of this, but it offered no practical solution for their own mounting problems. The production numbers alone told a story that gun caliber and armor thickness could not obscure. American factories produced 49,324 Sherman tanks between 1942 and 1945. This astounding total came from 11 different manufacturing facilities, each rigorously applying the mass production techniques pioneered in the American automotive industry. The Chrysler-Detroit tank arsenal led all producers, contributing nearly 18,000 vehicles. This single facility encapsulated the staggering scale of American industrial mobilization. The site had been farmland in 1940. By 1942, it had transformed into the largest tank factory in the world, encompassing over 1 million square feet of floor space. Workers who had previously built automobiles quickly learned to construct tanks within weeks. The assembly line methods perfected by Detroit automakers translated directly to armored vehicle production. The arsenal operated ceaselessly, around the clock, in 3 shifts. Tanks moved continuously down assembly lines, just as cars had, with components added at each station until a completed vehicle rolled off the end. Raw steel entered one end of the factory, and finished Shermans emerged from the other at a rate that would have seemed utterly impossible to German planners, who conceptualized production in terms of highly skilled craftsmen building individual vehicles. This single facility, in most war years, outproduced the entire German tank industry. Fisher Tank Arsenal contributed over 11,000 Shermans. Press Steel Car Company built more than 8,000. American Locomotive produced 2,300. Ford Motor Company added nearly 1,700, despite primarily focusing on other critical war production. Lima Locomotive Works, Baldwin Locomotive Works, Pacific Car and Foundry, and Federal Machine and Welder completed this vast production network. Germany's response to this deluge was severely hampered by its limited industrial capacity, relentless strategic bombing, and design choices that stubbornly prioritized individual quality over sheer quantity. Total Tiger I production from August 1942 through August 1944 amounted to approximately 1,350 vehicles, all originating from the Henschel factory in Kassel. When Allied bombers annihilated 95% of the Henschel plant's floor space in September and October 1944, the production of the Tiger II was irrevocably devastated. Fewer than 500 of these formidable tanks were completed before the war concluded. Panther production, dispersed across manufacturers like MAN, Daimler-Benz, and MNH, totaled roughly 6,000 tanks, despite being Germany's highest priority armored vehicle program from 1943 onward. The Panzer IV, Germany's most numerous tank and the backbone of its armored forces for much of the war, achieved a production total of approximately 8,500 vehicles from 3 manufacturing facilities. The arithmetic of this industrial contest was devastatingly clear. For every Tiger Germany managed to build, America produced 37 Shermans. For every Panther, 8 Shermans rolled off American assembly lines. The Germans could theoretically win every tactical engagement by a factor of 3-1 and still be overwhelmed by the sheer volume of American production. Even at exchange rates of 5-1, a ratio German tankers rarely achieved consistently. The mathematics overwhelmingly favored the Americans. The cost differential further exacerbated the problem. A Tiger I cost 250,800 Reichsmarks to produce. Early production vehicles, before manufacturing efficiencies were implemented, ran as high as 800,000 Reichsmarks. A Panther cost 117,100 Reichsmarks. A Panzer IV cost 103,462 Reichsmarks. Even the Sturmgeschütz III, Germany's most economical armored vehicle, still cost 82,500 Reichsmarks. German industry expended immense resources to produce a relatively small number of exceptionally capable vehicles, while American industry mass-produced good enough vehicles in quantities that defied comprehension. The resources consumed by a single Tiger could have produced multiple Panzer IVs. The resources devoted to one Panther could have yielded multiple Sturmgeschütz assault guns. But German military culture relentlessly demanded the best, and the best often proved to be the enemy of enough. The strategic implications extended far beyond simple numerical comparisons. German tank losses were effectively permanent. Every Tiger destroyed represented months of factory production that could never be recovered. Every Panther lost in combat or to mechanical failure was an irreplaceable asset, given the severe constraints on German industry. American losses, conversely, were temporary setbacks. Every Sherman destroyed was replaced by new production within weeks. The assembly lines never ceased. The convoys of ships continued across the Atlantic. The flow of new vehicles was relentless, transforming a temporary disadvantage into an enduring strategic superiority. This created a fundamental asymmetry in how the two sides could conduct the war. Germany was compelled to conserve its armor, deploying it cautiously for decisive engagements where the odds were overwhelmingly favorable. America could afford to employ its armor aggressively, accepting losses that would have crippled German formations, because replacements were always, inevitably, on their way. Albert Speer, who became Reich Minister of Armaments in February 1942 and significantly increased German war production through rationalization and the ruthless exploitation of forced labor, later characterized the conflict as a contest between two fundamentally different systems of organization. Germany's approach, which Speer termed overbred, demanded exacting requirements and produced small numbers of technologically advanced, high-end systems. America's approach, Speer observed, relied on the art of improvisation, yielding vast quantities of equipment that was good enough to achieve the mission, even if it did not excel in every individual category. The reliability gap proved more decisive than any theoretical difference in firepower or armor protection. German tanks were undeniably magnificent when they functioned properly. The pervasive problem was their frequent failure to do so. The Panther made its combat debut at the Battle of Kursk in July 1943, the largest tank battle in history. German commanders had precipitously rushed the new tank into service, disregarding warnings from engineers that production models had not undergone adequate testing. The High Command desperately wanted Panthers at Kursk to exploit their perceived technical advantages against Soviet armor. They got Panthers at Kursk. What they did not get, however, were Panthers that could reliably fight. The results vindicated every concern the engineers had raised. Contemporary German reports documented the unfolding disaster in stark, clinical terms. Before reaching the first preparation area, 50% of vehicles were inoperative. Two-thirds of these failures were attributed to engine breakdowns. The remaining third suffered from transmission and steering failures. Panthers were breaking down during the road march to the battlefield, not in direct combat against Soviet tanks. Within a week of combat, the original force of over 180 Panthers had been reduced to approximately 40 functional tanks. The operational readiness rate stood at barely above 16%. The most technologically advanced tank in the German arsenal could not even drive to the battle without breaking down, creating an immediate and crippling tactical deficit. While Soviet tankers destroyed some Panthers, German maintenance issues destroyed far more. These problems persisted throughout the war, despite continuous engineering efforts to address them. Panther operational readiness rates in 1944, after more than a year of production refinements, averaged 54% across all fronts. Monthly rates showed only gradual improvement as manufacturing matured. In February, only 37% of Panthers were combat-ready. The rate climbed to 50% by April and reached 78% in May, before fluctuating through the summer and fall. At no point did Panther operational rates consistently exceed 80%. The Sherman, by stark contrast, achieved operational readiness rates approaching 85% under comparable conditions. American tank crews could confidently expect their vehicles to start, run, and fight when ordered into action. This consistent reliability was not accidental. It was the direct outcome of design decisions that prioritized maintainability over maximum performance, of manufacturing processes that emphasize consistency over artisanal craftsmanship, and of a logistics system specifically engineered to keep vehicles running, rather than waiting indefinitely for specialized, elusive repairs. Soviet evaluations of Lend-Lease Shermans confirmed American reliability data. The Soviet 6th Guards Tank Army, which operated M482 diesel Shermans alongside their own T-34s, determined that their American tanks had a service life of 2,000 to 2,500 kilometers, comparable to their indigenous vehicles. Engines required inspection at approximately 100 operating hours and could run for 250 to 300 hours before requiring major maintenance. Soviet crews genuinely appreciated the Sherman's reliability, even as they acknowledged its vulnerability to German guns. The cascading consequences of unreliability multiplied across German armored formations as the war progressed and maintenance resources became increasingly scarce. A meeting of the Panzer Commission on January 23, 1945, documented the full scope of the crisis in terms that revealed the desperate situation. The assembled officers reported 370 defective Panther final drives awaiting repair or replacement. They reported 500 defective Panther 4 drives that had failed even before an eastern offensive could commence. They reported roughly 100 Tiger failures of various types. These were not vehicles destroyed by enemy fire. These were vehicles abandoned because their own components had simply failed. A German general stated that an orderly utilization of tanks was simply impossible under these conditions. The troops, he added, lose their confidence and in some situations abandon the whole vehicle just because of this problem. German tank crews, who should have been fighting the enemy, instead found themselves fighting their own equipment. Crews who should have been confident in their machines learned to anticipate breakdowns and plan for them, creating an inescapable mental burden that undermined combat effectiveness. The psychological impact of unreliability compounded its practical effects, becoming a quiet, yet relentless, internal enemy. The 101st SS Heavy Panzer Battalion provided a grim illustration of this problem in microcosm. When alerted for deployment to Normandy on June 7, 1944, just one day after the Allied invasion, the battalion theoretically possessed 45 Tiger tanks, with 37 initially listed as operational. The road march from their assembly area near Beauvais to the combat zone around Villers-Bocage should have been a routine movement of approximately 165 kilometers over French roads. Instead, a combination of mechanical breakdowns and relentless Allied fighter-bomber attacks reduced the available force to approximately 6 operational vehicles by the time they reached the battle area on June 13th. Tigers broke down repeatedly along the route. Recovery vehicles struggled mightily to tow the massive tanks. Air attacks destroyed or damaged vehicles that had stopped for repairs. An entire heavy tank battalion had been rendered largely ineffective, reduced to a handful of operational vehicles, even before firing a single shot at the enemy. Michael Wittmann's legendary action at Villers-Bocage on June 13th demonstrated what a skilled crew in a powerful tank could accomplish when it actually reached the fight. In a matter of minutes, Wittmann's single Tiger destroyed more than a dozen British vehicles, including tanks, armored cars, and carriers. This action became legendary, cited for decades as irrefutable proof of German armored superiority. But the broader context starkly revealed the crippling limitations of German doctrine. The 101st SS Heavy Panzer Battalion had 45 Tigers on paper. It had 6 in action. The remaining 39 were either broken down, destroyed by air attack, or still struggling toward the front, immobilized along the roads. Wittmann's individual brilliance could not possibly compensate for the systemic failures that left the majority of his battalion's combat power sitting uselessly along French roads. A stark reminder that the best tank meant nothing if it couldn't reach the battle. The Battle of Aricourt in September 1944 offered the most comprehensive test of Sherman versus Panther in sustained combat. This engagement, fought in the Lorraine region of France, became the largest American tank battle on the Western Front until the Battle of the Bulge 3 months later. The German 5th Panzer Army committed 262 tanks and assault guns to a desperate counterattack intended to halt Patton's Third Army. This force included 107 Panthers, 75 Panzer IVs, and 80 assault guns, substantial numbers by late war standards. Opposing them was Combat Command A of the 4th Armored Division, equipped with M4 Shermans and M18 Hellcat tank destroyers. The German forces entered the battle suffering from crippling disadvantages that bore no relation to their equipment specifications. The 111th and 113th Panzer Brigades had been formed only weeks before being thrown into battle. The 113th, for instance, was organized on September 4th, 1944, just 15 days before it was committed to action. Crews had severely shortened training schedules and demonstrated little proficiency in tactical maneuvering. Many units had never operated together before. Some Panthers were still receiving final adjustments from factory representatives when the attack orders arrived. The 5th Panzer Army lacked integral reconnaissance units and was forced to advance blindly into American positions. German commanders had no precise knowledge of where the Americans were, their strength, or their deployment. They attacked expecting to find scattered rear area units and instead encountered experienced armored formations that had been fighting continuously since Normandy. American tactics ruthlessly exploited every German weakness, turning their perceived shortcomings into strengths. Shermans leveraged their faster turret traverse to engage targets more quickly than Panthers could respond. A Sherman's turret could rotate a full 360 degrees in 15 seconds. The Panther required more than twice as long for the same maneuver. In close-quarters combat, where fractions of a second determined who fired first, this difference proved decisive. American crews fought from concealed defensive positions that effectively negated the German advantage in long-range gunnery. Panthers and Tigers excelled at destroying enemy tanks at distances of 1,000 meters or more, but the rolling terrain around Aricourt offered few such extensive sightlines. Combat frequently occurred at ranges of 300 to 500 meters, where the Sherman's gun could penetrate Panther side armor and where faster reaction times, not superior optics, held the greater importance. A thick morning fog on several days allowed American tanks to close to ranges where even frontal engagements favored the faster-firing Sherman. German crews, expecting to engage at long range, suddenly found American tanks emerging from the mist at point-blank distance. Their extensive training and theoretical understanding failed them. Faster American reactions succeeded. On September 19th, American Shermans flanked and destroyed 11 Panzers, effectively using the fog as concealment. Captain Lameson's Company C of the 37th Tank Battalion arrived at a defensive position on a ridgeline a mere 3 minutes before 8 Panthers appeared from the mist. Those 3 minutes made all the difference. Lameson's tanks were positioned and ready. The German tanks were advancing blindly. Lameson's crews engaged immediately, knocking out 4 Panthers before the German crews could even identify targets and return fire. The Americans then withdrew over the ridge, repositioned several hundred meters south, and reappeared to engage the surviving Panthers from a new angle. The remaining German tanks, already disoriented by the loss of half their number, were systematically destroyed. The battle raged for 11 days as German forces launched repeated, desperate attempts to break through American positions. Each attack unfolded in a similar, predictable pattern. German tanks advanced without adequate reconnaissance. American forces detected them and established ambush positions. Combat invariably occurred at ranges that negated German technical advantages, and German losses mounted relentlessly. When the battle finally concluded on September 29th, German forces had lost 86 tanks confirmed destroyed, with an additional 114 damaged or broken down. Only 62 of the original 262 vehicles remained operational. American losses totaled 25 tanks and 7 tank destroyers, a mere fraction of German casualties. The aftermath of Ericourt was as revealing as the battle itself. American maintenance crews quickly recovered damaged Shermans from the battlefield, returning many to service within days. German recovery efforts salvaged some vehicles, but they critically lacked the spare parts and workshop capacity to repair them swiftly. The American force that had fought at Ericourt was back to full strength within 2 weeks. The German force that had attacked them never recovered, suffering a permanent operational setback. The lessons were clear to anyone willing to observe them. Superior equipment meant nothing if it could not be kept running. Tactical advantages meant nothing if units could not consistently generate enough combat power to exploit them. The most powerful tank in the world was utterly worthless if it sat in a repair depot while the enemy advanced. Military historians have since cited Ericourt as a stark demonstration that crew quality and tactical training can often be far more crucial factors in determining the outcome of a tank battle than the technical specifications of the tanks themselves. The Panther was demonstrably superior to the Sherman by every metric German engineers valued, but paper specifications did not fight at Ericourt. Untrained crews in mechanically unreliable vehicles fought against experienced American tankers who thoroughly understood their equipment and knew precisely how to exploit its advantages. German officers who survived the war offered assessments that directly contradicted the pervasive mythology of German tank superiority. General Otto von Manchefeld, who commanded the 5th Panzer Army during the Ardennes Offensive and was recognized as one of Germany's most respected armored warfare experts, provided extensive interviews to the British military historian B.H. Liddell Hart after the war. Manchefeld emphasized that much more importance should be placed on the speed of the tank on the battlefield than was generally believed before and during the war. The capacity to move quickly, to reposition faster than the enemy could react, to concentrate force at decisive points. These factors, he argued, mattered as much as firepower and protection. Maneuverability, Manchefeld declared, develops into a weapon and often ranks equal to firepower and armor protection. This was precisely the principle American designers had embraced and which German designers had largely dismissed. The Sherman prioritized mobility and reliability over maximum combat power. It could reach places German tanks could not, remain operational when German tanks broke down, and concentrate faster than German formations could respond. The Tiger and Panther, conversely, prioritized overwhelming firepower and impenetrable protection, optimizing for the decisive engagement while neglecting the countless other factors that determined whether tanks even reached the battlefield ready to fight. Albert Speer himself acknowledged the Sherman's unexpected capabilities in his post-war memoir, Inside the Third Reich. Describing reports from the Italian front, where American armor operated in mountainous terrain that theoretically should have favored defenders, Speer candidly recorded what German commanders observed. The Sherman climbs mountains our tank experts consider inaccessible to tanks. Speer noted, one great advantage is that the Sherman has a very powerful motor in proportion to its weight. Its cross-country mobility on level ground is, as the 26th Panzer Division reports, definitely superior to that of our tanks. This was a remarkable admission from the man solely responsible for German war production. German tank experts had meticulously designed vehicles optimized for destroying enemy armor in direct combat. They had not designed vehicles that could consistently keep pace with Sherman's across the immensely varied terrain of a continental war. American tanks went to places German tanks could not follow. American tanks arrived at battles German tanks never reached. The distinct institutional cultures that generated these different approaches proved as critical as the tanks themselves. American military doctrine emphasized adaptability and continuous improvement. After-action reports from combat units flowed back to training establishments and design bureaus within weeks. Problems identified in the field were rigorously analyzed by engineers, who then revised specifications and modified production. The Sherman that rolled off assembly lines in 1944 incorporated hundreds of improvements based directly on combat experience in North Africa, Sicily, and Italy, a testament to an iterative design process. German military culture, however, had calcified around fixed doctrines and personal loyalties that actively discouraged honest assessment of problems. Initiative in questioning established approaches was suppressed. Failure to achieve assigned objectives was often fatal to careers. Engineers who identified fundamental design problems with the Panther's transmission were instructed to find solutions, not to challenge core design decisions that had been personally approved by senior officials and endorsed by the highest levels of the Reich. Adolf Hitler exacerbated this rigidity through constant, often erratic, interference in weapons development. He demanded changes to tank designs based on intuition rather than sound engineering analysis. He insisted on heavier armor and larger guns, even when engineers repeatedly warned that existing automotive components simply could not support the additional weight. Commanders quickly learned that disagreeing with decisions that had reached the Führer was career-ending at best and potentially fatal at worst. The honest assessments that might have corrected German tank design were systematically suppressed in favor of reports that told leadership precisely what it wanted to hear. Problems were minimized. Failures were routinely attributed to factors beyond control. The systematic analysis of what was going wrong and why, a hallmark of American military institutions, was inherently dangerous in a system where acknowledging problems could be interpreted as defeatism. The American system, by contrast, appeared chaotic. Different units developed diverse solutions to similar problems. Coordination between branches of service was often imperfect. Arguments about doctrine and equipment continued throughout the war. Yet, this very chaos was productive. Ideas that proved effective survived, rapidly spreading throughout the force. Ideas that failed were quickly abandoned, without regard for whose reputation might be attached to them. The organization as a whole became increasingly effective, even when individual components struggled. By the spring of 1945, the profound consequences of these different approaches had become undeniable. American armored divisions advanced across Germany with operational readiness rates that German commanders could only envy. Sherman tanks that broke down were repaired and returned to action within days. Spare parts flowed forward through a logistics system that continued to function despite the chaos of mobile warfare. Replacement vehicles arrived from ports where ships delivered a continuous stream of new production, creating an unyielding tide. German tank formations, meanwhile, had largely disintegrated under the sheer weight of their own complexity. Vehicles that should have been fighting sat immobilized in repair depots, awaiting parts that would never arrive. Crews abandoned Panthers and Tigers not because of enemy fire, but because transmissions failed or engines seized or final drive stripped, leaving them marooned. The magnificent machines that were supposed to turn the tide of the war instead rusted in fields and forests across the Reich, monuments to a philosophy that had, in the end, prioritized the wrong things. The men who had once dismissed American industrial capacity as mere propaganda now watched American factories